So yeah, welcome to CS 161 lecture number 4. Last time we talked a bit about memory safety vulnerabilities in C, and today we're going to talk about how we prevent them and stop attackers from exploiting them. So these are some of the memory safety vulnerabilities we went over last time: buffer overflows, which allow attackers to write past where they're supposed to; integer memory safety vulnerabilities, which have to do with representing integers in C, so usually either signed unsigned vulnerabilities or integer overflow vulnerabilities. We also have format string vulnerabilities, which are very powerful. They allow the attacker to basically read or write to any memory address they want. We have some memory vulnerabilities that take place on the heap. And at the end, we talked a little bit about how we write robust exploits and how it can be really difficult. So this is not tomorrow, this is today. Today, we're going to talk about some memory safe languages, how we write memory safe code, some tools that we can use to build secure software, and then we'll get into exploit mitigations, which are really the meat of today's lecture: how we prevent vulnerabilities from actually being exploited. And we'll talk a bit about how we combine mitigations at the end. So we've seen how memory safety vulnerabilities can be dangerous. They allow the attacker to execute pretty much any code that they want. And a good question that we ask ourselves is, why does this happen? Well, for one, programming languages that we use aren't often designed for security. Nowadays, we have memory safe languages, but when we're working with something like C or C++, those allow us to have these vulnerabilities creep into our code. Oftentimes, the programmers also aren't security aware, so maybe they're not used to writing secure code and they add vulnerabilities because they don't know any better. Sometimes we'll write code, even if we are conscious of security, we'll write code that doesn't have security designed in from the start. So maybe you wrote some code just for a project for fun and you didn't care about security, and all of a sudden that code is incorporated into some important code base for something. So yeah. And finally, this is, I think, the most often reason, but programmers are humans and humans make mistakes. Again, I've made mistakes in my code before that in theory would allow an attacker to exploit it and run their own malicious code, but these are all reasons that allow vulnerabilities to creep in. We have a couple of approaches for defending against this. The most important one that we'll talk about is to use a memory safe programming language, to use a safer programming language. We'll also talk a bit about how we write memory safe code and some tools that we have for patching and analyzing insecure code to make it secure. And finally, we'll talk about mitigations again that allow us to have it such that even if vulnerabilities exist in code, the attacker can't exploit them. So first, we'll talk about memory safe programming languages. Memory safe languages are languages that are designed to check the bounds on anything that you read or write from memory and prevent memory accesses that aren't supposed to happen, prevent undefined memory accesses. By design, these languages are not vulnerable to memory safety vulnerabilities. Sort of the definition of a memory safe language is that it does not allow you to make these errors. This is the only way to actually stop 100% of memory safety vulnerabilities, because even if you have programmed in C since you were 2 years old, you will still eventually make a mistake that allows a vulnerability to slip in. So this is the only way to actually stop 100% of vulnerabilities, is to use a language that stops them from happening in the first place. Some examples that you might have come across, or maybe you will come across, are Java, Python, C#, Go, and Rust. We'll use Go in this class later on in project 2. Basically, all languages aside from C, C++, and Objective-C are memory safe. So most of the time, you're probably going to be writing in a memory safe language. But this starts to bring up the question of, why do people use non-memory safe languages in the first place? And some of us might have heard these reasons. Does anyone? Yes. Before I even got to ask the question, we got an answer in chat. Performance. Yes, the P word in this class. And there's some basis for this. If you think about something like C, where we have malloc and free, malloc almost always runs in constant time because all we're asking it is to allocate memory. We're not asking it to do anything else from it. for us. Sometimes it might have to ask for more memory from the operating system, but most of the time it runs in constant time. Compare this to something like Java. In Java, we have something called a garbage collector, so it can free memory without us ever having to directly tell it what pointers to free. And it can run at any point in time. So I might be halfway through executing a piece of code, and all of a sudden the Java runtime says, oh, I need to go and clean up some memory. So I'm just going to add a 10 to 100 millisecond delay or so. So this has some basis in reality, but nowadays is actually more of a myth than anything. For most applications, you're not going to see that much of a difference in using a memory-safe programming language. The only real exceptions to this might be if you're writing an operating system. You can't afford to have that 10 to 100 millisecond delay. If you're writing some really high performance game engines, or if you're on some embedded systems because you can't afford to wait for the garbage collector to give you memory, you need to specify that this piece of memory is free right now and it can be used in the future. But unless you're one of these three, or maybe a couple other exceptions, you really don't need to use C, and you really, really don't need to use C++. It's not a correct thing to say that C is faster because it is memory unsafe. In the past, languages have made trade-offs between security and performance. In Java, for example, each array check actually has a comparison, like, is this index smaller than the length, and I guess greater than or equal to 0. But nowadays, it's actually not that significant. In a language like Rust, which can actually achieve speeds that are basically the same as C after you add in all the runtime checks, you basically have the same performance. And in something like Go actually has an even better concurrency model than C does. So Go lets you perform even faster than C in some cases if you're writing a heavily threaded application. And yeah, I mentioned this already, when you write secure C with all these bound checking, you're basically writing the same code that you would get in Rust, but it takes you a lot longer to write. So you don't need to pick between security and performance. Nowadays, you can actually have both. My slide is frozen. I'm not sure why. Hello? All right, slide 11. And the other thing to think about is that your programmer time matters too. The time that you're going to gain from writing in a memory-safe language is probably more than the couple milliseconds that you're going to get in performance once your code is done. And it's definitely going to save you a lot of headaches in the future. The Solr languages also have libraries that will plug into fast, secure C libraries anyway. So, for example, NumPy in Python, some other developer has already gone through all the work of making NumPy written in C and making it secure and making it fast. You just have to use the memory-safe language, Python, to interact with it, and it will automatically give you a speed up anyway. If you were in 61C and you had a project 4 that had to do with optimization, you might have actually done this yourself in the form of another Python library. The real reason nowadays that languages like C tend to be used is legacy. So when you're dealing with a really large and a really old code base, say you're working with a web server that's been developed for the last 30 or 40 years, that's almost always going to be written in C. And if you're working with software that's already written in C, chances are you're going to keep writing C to build on that software. It's easier than starting from scratch and, say, rewriting a web server entirely in, say, Java or Go or Rust. Basically, the saying here is, if you start a project and code is written in a given language X, then the new code for that software is also going to be written in that language X. A good example of this is iPhone. So if anyone's ever developed an iPhone app before, oftentimes you might have used a language called Objective-C. I'm getting ahead of myself, so I'll go back for a moment. When Apple created the iPhone, they modified their operating system to run on a phone. This was really way back in the day. So even though there's no code that dates back to 1989 on your iPhone, there's still a lot of the programming concepts there. And one of the languages that was used was Objective-C. So nowadays, when we're writing apps, we're still using this old language, Objective-C. Nowadays, there's a new language called Swift, which, again, if you've developed an iPhone application yourself, Swift is a language that you might have actually used instead of Objective-C. But the takeaway here is that the reason we use non-memory safe languages is because they've been used in the past and they're still being used for legacy reasons. So that's great. If you're starting a new project, highly recommend not using C, not using C++. Use something with memory safety and you'll probably be fine. But if you're stuck with C, we have a couple of techniques that we can use to make sure you're writing memory safe code. Defensive programming is the idea that you're always adding checks to your code, even if you're sure that, say, oh, I know this pointer is not a null pointer, just check for it anyway. You never know if some programmer in the future is going to maybe import your library and try to call it with a null pointer. So the idea is it's better safe than sorry, but it relies on the programmer to do something correctly. And if we think back to consider human factors, oftentimes humans cannot be relied upon to do things correctly. In general, the best thing to do if you are trying to write code that does a thing is to see if someone else has already written code that does that thing and does it safely. So if I'm trying to write, say, secure code for encryption, I'm not going to write that code myself. I'm going to import a library where someone else has already written that encryption code for me. Those functions will definitely, well, when they need to, they'll check bounds. And in the C standard library, we talked about a couple of functions that are already safe. For example, using fgets instead of gets, using strncopy or strlcopy instead of just strcopy, and using snprintf instead of sprintf. Again, these are all functions whose man pages you can look up on your own. We're not too concerned with having you sort of produce memory safe code as part of this class, but it's something that you need to know because it's important. This also relies on programmer discipline, or it relies on tools that check your program. So that's what we're going to get into next. No, it's not. Sorry, I must have reordered these slides at some point. Another technique that we have is that you can structure user input. So what you want to do here is constrain the user as much as possible so that the user can only enter an input that is unlikely to be malicious. So for example, when you're asking a user to input their age, you should only allow digits. And you can imagine that it might be harder to construct a malicious payload, especially shellcode, that only uses 10 possible bytes, the bytes that represent the characters 0 through 9. Skipped a little bit here, but you should also implement a reference monitor. So this is going to be part of your TCB, and all input has to pass through this and be validated to fit the constraints on the user input before you continue. There are also more theoretical aspects of how you can reason about your code. This used to be in scope, but we used to teach a set of skills, I guess, that are called preconditions, postconditions, and invariants. And basically, they are guarantees from one part of a code to another that says, I guarantee that, for example, this pointer is not null, or I guarantee that the length parameter is going to be smaller than the size of the input. So it's a little bit tedious. It's very tedious, and it's not really something that we see in practice nowadays. So now it's out of the scope of the class and you don't have to worry about it anymore. But this is something that exists if you ever happen to come across it. Some techniques that we have for building secure software, and this is where I'm getting back into tools. We have runtime checks. So I mentioned in something like Java, anytime you access an array in Java, it's going to run a check to make sure, oh, this index is a valid index for the length of this array, which is also something that's tracked as part of the array object. But you can imagine that there's a little bit of performance overhead here. And the idea is that once we detect that something has gone wrong, we're just going to crash instead of letting the invalid access succeed. Another idea that we have is we can check code and make sure that it's doing what we expect. So it's the runtime behavior of the program is what we're expecting it to do. So for example, if we know that we're only going to call function A, then function B, then function C, if at any point we see function C before A or B has been called, we might imagine, oh, something has gone wrong here, because that's never supposed to happen in the normal execution of a program. Another example that you might have is, you know, your code is never going to run a function called execv. It's a common function that's used in shellcode. But at some point you notice, this program called execv, this is probably an issue. And the issue here is that by the time you detect that your program is acting in a strange and probably malicious way, it's probably too late for you to stop it and some damage has already been done. But if you catch it, you probably want to crash the program. Another technique is to contain potential damage. So when we deal with modern software, oftentimes we're going to be working with sandboxes and virtual machines. These are basically emulated computers, and your program runs inside that emulated computer. So if the program becomes malicious, the program will still be stuck inside that box that we've contained it in, and it won't be able to spread to the rest of the system. This is related to separation of privilege. It's also related to least privilege. You can think about on your own what the other security principles that would apply here would be. Another more technical tool that we have is bug finding tools. So we can write software that will actually analyze our code and spit out, hey, looks like there's a memory safety vulnerability here because, I don't know, you're not checking the value of this index. This is a great way to find tools. We've caught many bugs using these tools in the past, as long as the tools don't spit out too many false positives, too many false bugs. It detects a bug when there isn't actually a bug there. If it does detect too many bugs, then suddenly we're wasting programmer time and the programmer is not going to use your tool anymore. You can, again, think about consider human factors, but you should make sure that your bug finding tools are only finding bugs that actually exist. Code review is the idea of hiring someone else to look at your C code. So I've run into many situations where I code something and there's a bug and I just can't find it. And I ask someone else to take a look at it and they immediately figure out, hey, you're using the wrong input here. And I'm like, why didn't I see that? So the idea is the same thing here. Hire someone else, usually a professional, to look over your code and see if they can find memory safety errors. This can be very effective. There are entire companies built around checking and auditing software, but it's a business. It can be expensive. You can also scan for vulnerabilities. So oftentimes there are patterns that programmers will make that we know are vulnerable. Maybe they again have forgotten to check their bounds on something. So we also have tools that will check for certain patterns and detect when the programmer makes them and basically send up a flag. Finally, and I think this is the most fun one, we have the idea of penetration testing or pen testing. So I mentioned this all the way back in lecture 1 when I talked about it's okay to break into someone else's system if they've given you explicit permission. And this is a good way of testing if there are vulnerabilities, because basically they're trying to break into your system. They have to find the vulnerabilities to do that. And once they do it, or if they can do it, preferably they can't, but then you take notes on how they did it and patch up those security holes. Testing can be difficult. We're testing for the absence of vulnerabilities, which is inevitably difficult to prove, because it's really difficult to prove that something doesn't exist. Normal inputs are rarely going to reveal security vulnerabilities, mainly because programmers are bad at thinking about these edge cases. So how can we test programs for memory safety vulnerabilities? One of the ways that's used pretty often is fuzz testing. So you will run a program 1,000,000 times with 1,000,000 random inputs. And if that gives you a pretty good chance at finding certain bugs that you might have missed because your own tested inputs weren't very comprehensive. So this literally sends random data to the program and see if it can break it in weird ways. We can also use something like Valgrind to find memory leaks, which often end up as security vulnerabilities as well. And corner cases, these are also tests that you should write yourself to make sure you're testing weird cases and not just normal inputs. We can tell that we found a problem if the program crashes because it's seg faulted or because of any other reason, basically. And how do we know if we've tested enough? Can be more difficult to figure out. The tools that we have in this case are code coverage tools, which basically check which parts of the code that we've run and which parts of the code that we haven't. And the idea is if during our testing we ran a certain piece of code, then we can infer that, okay, our tests were good enough at testing this part of the code. Modern software will often import a lot of different libraries. So nowadays we're dealing with not just our own code, but code that a lot of other people have written. So these libraries of other people's code are often updated with security patches because they have security vulnerabilities. So it's not important to just make sure your own code is secure. You also have to make sure you're keeping up to date with updates, security patches. The difficult part about this is you have to do it. When you update, sometimes you have to restart production systems. Anyone who has a Windows computer is familiar with the idea that Windows will just restart itself to apply patches. It can break things. So if a programmer updates a library and changes the expected functionality, then you'll end up breaking any program that relies on that library. And it's just a burden. If I have to log into a server every day and update that server, it just becomes something that I don't want to do anymore. And then inevitably I'll forget to do it a couple days and it's just a burden. The quote we have here is the patch treadmill never stops. I'm going to skip over these stories in the interest of time. They're blue slides, so you don't have to worry about them. And I've already gone over the main points of patching stories of patching systems in the previous slides. Are there any questions on any of this before we get into mitigations? I know it's a little bit more conceptual, so hopefully it didn't give you too much trouble, but feel free to drop by office hours or anything if you do have any questions. Okay, so we've talked about how do we produce secure code. We've talked about memory safe languages, and we've talked about the tools to make unmemory safe languages probably not have vulnerabilities. But we still want to consider defense in depth. Consider this scenario. You've just joined a team at some large company, and they've just handed you a giant code base that is written in C. And it was written by someone who really didn't care about security. They used get-s and strcpy everywhere, and it's just bad. We want to protect even this code. We know that, okay, the programmer messed up, but we still want to come up with ways to make it harder to exploit this code. These defenses are called exploit mitigations, and we call the process of using them code hardening. They harden code, as in they make it more difficult to exploit, even though it's still vulnerable. They basically all find ways to turn attempted exploits into crashes. So again, we talked about this last time. Oftentimes when a program crashes, it's not good, but in computer security, it's better to crash a program than to allow the attacker to exploit it. These mitigations can be pretty cheap, so it doesn't take too much extra code. It doesn't add too much of a performance penalty, but some of them will have costs associated with them. And we'll go through the efficiency of each one as we go through them. So mitigations can be a bit of an arm race because we're developing these defenses in order to stop attackers from exploiting things. And then the attackers are going to develop ways to defeat the mitigation, and then the security researchers find ways to mitigate things in different ways, and the attackers find ways to defeat those. So it's a bit of an arm race. It goes back and forth. They make attacks harder, again, but it doesn't make them impossible. So remember that the only way to prevent buffer overflow attacks is to use a memory safe language. But because of defense in depth, we still want to use these anyway. So I'm pulling back this slide from yesterday, yesterday. And this is the idea of this is the flow of how we execute attack in the first place. First, we need to find a memory safety vulnerability. Then we need to write shellcode at a known address. Then we need to overwrite the RIP with that address. Then we need to return from the function. Then we're going to start executing our shellcode. What we're going to do is we're going to go through mitigations that basically attack each one of these steps. We're not going to go through one because the only way to stop finding vulnerabilities is to use the memory safe language. And we're not going to go through 4 because returning from a function is something that's going to happen anyway. Okay, the first one we're going to talk about is non-executable pages. So this one will stop step 5. This one stops the malicious shellcode in memory from actually executing. The idea here is that most programs aren't going to need pieces of memory that you can both write to and execute. The only scenario where you might need this is something like a just-in-time compiler, which compiles code as it's running it and then runs that code, or something like self-modifying code, which is awful. But sometimes it does happen where a programmer writes code that changes itself as it's running. So it does happen, but it's not very often. So what we're going to do is we have 2 main categories of code. We're going to have the stack, heap, and data sections, which are going to be writable, but we're going to make sure, okay, we can't execute these bytes. And then we have the code. We're going to say, okay, we can execute these bytes, but we're going to make sure we can't write to those bytes because we don't want the attacker writing malicious shellcode there. We can actually implement this using page tables. So if you took 61C, you went through this idea of virtual memory. And in virtual memory, we have a page table that will say, okay, this address, XYZ, actually translates to the hardware physical address of, I don't know, ABC. Page tables also give us a way of saying, okay, this page of memory should be only writable, and this page of memory should be only executable. So because this is basically already implemented, it doesn't have any overhead. We can actually just turn this on, and the program will run the same as before. It's known by a couple other names. We are trying to make sure that we call it the same thing in all materials this semester, but it's possible that it might slip through a couple times. So you might see it around or on the internet as W XOR X, write XOR execute, DEP, which is data execution prevention, which is the name used by Windows operating systems, or the no execute bit. So that's just the name of the bit itself when you don't want to execute a piece of code, a piece of data. All right. That's the idea in theory. And in theory, it sounds great because then it's like, oh, the attacker doesn't have a way of writing an exploit and then executing that exploit. But it doesn't help the idea that the attacker can still use existing code in memory. A lot of programs are going to load a lot of functions. Basically, it's going to load the C library, and the C library has a lot of functions that we can take advantage of. The 2 main subversion techniques that we're going to look at are return to libc and return-oriented programming. And I won't go through these definitions now because I'll go through them in more depth on the next couple of slides. So, return to libc. Per the x86 calling convention, each program is going to expect the arguments to be right above the RIP, because right before I call a function, I'm going to push the arguments onto the stack, and then I'm going to execute the call instruction to actually push the RIP on. So any function is expecting the arguments to come right above the RIP. If we jump to a function without using the call instruction, we're literally just using, say, a jump instruction, then returning to the beginning of another function means that it's still going to look 4 bytes above whatever the current ESP is. So remember, the function expects the ESP to point to the RIP, so it's expecting to look 4 bytes above the ESP to look for its first argument. The system function, which is a function that exists in older versions of the C language, but I think it was taken out. I actually don't remember. It might not have been. Well, the system function lets us execute a shell command. If we have a car array that says rm//, and then we execute the system command on that car array, it's going to execute the command rmrf/, which, if you're not familiar, deletes your entire file system, which is bad. So this is what the memory of this program might look like. This is just the C code for it. This is the code that's actually in memory, or at least it's the assembly representation of that code. And this is a stack diagram that we have on the left here. So I'm going to give you this exploit because it's a little bit hard to come up with on your own, but hopefully it will help make clear how it actually works. So we're starting by writing 24 dummy bytes, starting up name here. We write 24 dummy bytes to get to the RIP. Then we're going to say, okay, this points to the address of system. And I thought I fixed this error to point that way, but that's okay. So the RIP is the address of system. Then we have 4 more dummy bytes, and then we're going to write the address of this rmrf/ sequence. And then because it's a car array, we also need to place the bytes of that string somewhere in memory. All right. So what happens when we return from this? We've just finished executing call. This add instruction is going to basically deallocate the argument to gets. Then we're going to deallocate the stack frame. So ESP is going to move up to the EPP because we don't need anything here anymore. Then we're going to pop off the EPP. So this is the same thing as last time. We expected the SFP to be in this location. So we popped it off, expecting for the EBP to move back up to where it was before. But now it's just in the middle of nowhere because we overwrote those bytes with a bunch of dummy bytes. Now we're going to return. So now the EIP jumps to wherever the ESP was originally pointing. So it was originally pointing down here, and the EIP points to this system function. I see P in chat. I'm not sure if it's supposed to mean something. So we pop that address off, and now we're entering the system function. Remember, the system function expects its first argument to be 4 bytes above the ESP. So the ESP is now pointing at these 4 dummy bytes, and 4 bytes above that is the pointer to the character sequence rmrf/. So even though we didn't actually jump into the system function with a call instruction, the system function is still going to think, I must have been called. I'm expecting my first argument up here, and I see that it's rmrf/. So now I'm going to execute as if I've been called with that argument. And then the program goes and subsequently deletes all your files, and that is the end of this program. So even though we couldn't write any code ourselves and then execute it, we were able to take advantage of other code that was loaded into memory. Does this make sense? Any questions on this? All right. That's return to libc. We call it libc because libc is the name of the C standard library. Now we're going to take this idea and we're basically going to turn it up to its extremes. Instead of executing just a single existing function, we can still execute any code that we want if we chain together different pieces of code. We don't need to jump to the beginning of a function because every instruction has its own address. We could, in theory, put the RIP as somewhere in the middle of a function, and then we'll jump there and just continue executing. So we're going to call each chain of instructions that we execute because of a return a gadget. There's just a small set of assembly instructions that are somewhere in memory. These gadgets will usually end in a ret instruction, and I'll show you why in a moment. And the important thing to keep in mind is gadgets are not full functions. Again, we can jump into the middle of a function, and that will end in a return, and that will happen to help us out. So the strategy here is we're going to chain a bunch of return addresses that chain a bunch of gadgets together. And eventually, after executing all of those gadgets, it's going to be as if we've executed our original code. Yeah. And the ret instruction at the end of each gadget basically just means pop the next RIP off the stack and jump there and continue executing the next gadget. So again, hopefully this will be more clear in the next slide. So here is the shell code that we want to execute. This is really simple. This isn't actually malicious. Let's just use this as a really simple example. We have 2 instructions here. And let's just say somewhere in memory, we have these two functions. We have a foo, and then I cut it off a little bit. And then we have a bar, cut it off a little bit, and then these both end in red. So can you imagine how could we possibly execute a sequence of instructions using just return addresses that looks like this sequence of instructions? Does anyone have any ideas of what we could do? Bar plus 25 and then foo plus 10. Yes, exactly. So, oh, fascinating. These ellipses move over a little bit. That's okay, I'll fix it later. That's exactly correct. So we know that, okay, this move instruction is actually the same as the move instruction down here, followed by a return. This XOR instruction is the same as this XOR instruction down here, followed by a return. So we know if we jump here and then return to here and then return to somewhere else, then it's as if we just executed these two instructions together. So if we jump 25 bytes after bar and then jump 10 bytes after foo, we get the same thing as our malicious quote unquote shellcode. So here's what we're going to do. Our exploit is going to look like a times 24, just to get past everything that we normally get past, and then the address of bar plus 25, and then the address of foo plus 10. And that looks something like this. We fill all of the stuff that we don't need, and then this is our first RIP, and then this is our second RIP. So we're going to return as normal. Now we're at this return instruction, and we're going to jump to here. And then we execute this move instruction, and then we're at another return instruction. So even though this wasn't originally an RIP, return just says, oh, just pop the next address off the stack because I'm assuming that was the RIP. So now we're going to jump here and execute this XOR. And then we get to this instruction, and then presumably we have a longer chain of addresses until we get the full malicious behavior that we want. And it's just going to keep popping off RIPs until we get the desired result. Does it make sense how this works? It was a little bit more confusing, so it's totally fine to be confused about it, but yeah. All right. In that case, we'll talk. Yeah, yes. Para and I both did not understand when this was first taught. So gadgets can't be full functions because that would mess with the RIP. That depends. So remember, when we're in this class, you can assume that we're working with unoptimized code, and full functions will always mess with the ESP and mess with the SFP and all of that other stuff. But in optimized code, it's more likely that you'll just see like random sequences followed by a return address. So it's possible that you could use a full function, especially in optimized code, but usually you're not going to use the full function. Usually you're only going to use a part of it. All right. So if the code base is big enough, if it imports enough libraries, if there's just enough code that's floating around in memory, then usually you're going to have enough gadgets to do everything that you want. There are actually programs nowadays called ROP compilers that basically you upload your code or your binary that you want to exploit, you upload the shell code that you want to execute, and it's actually going to go in and compile a really long list of return addresses for you to input into the program, and it will automatically execute the chain of gadgets as if we just executed your shellcode. So these are programs that are actually really powerful, and they allow us to basically subvert non-executable pages in any way we want. It used to be a really high-level technique, but now it's really easy and really commonplace. If you go online and search ROP compilers, I think I did this recently, and there was one for specifically CSGO, which is a video game. But yeah, this is really commonplace nowadays, and it means that non-executable pages, while it's annoying sometimes for attackers, it's not that much of an issue. Your life is a little bit easier if you have executable and writable pages, but it's not going to be that much easier. All right. First mitigation down, we have 3 more to go. Stack canary. Before I get into stack canaries, any questions on anything else? I think I asked for questions recently, now that I think about it. All right. So now we're going to jump back in the sequence of events. We're going to find ways to prevent the RIP from being overwritten with the address of shellcode. The first one that we'll talk about is called stack canaries. So if you're asking canary, that's a weird term to use. It's because we used to, I don't actually know if we still do, but we have this idea of a canary in a coal mine. The idea is that miners often have to deal with toxic gas when they're working in the mines. So they actually bring a canary with them. A canary is just a small bird, and that bird is really sensitive to toxic gas. So if the canary passes out or passes away, the miners know that, oh, there's toxic gas in here. We should get out of here before we are affected by the toxic gas. The canary in a coal mine essentially thus is a sacrificial animal. The miners don't expect the canary to survive, but it's a sign that something else has gone wrong, and it allows the lives of the miner to be saved. So we're going to use the same idea. We're going to place some sort of value on the stack, and we're going to check if that value has somehow changed or if it's been affected. Then we're going to assume something has gone terribly wrong. We're just going to crash the program. The value doesn't matter. We just need to make sure it doesn't change. Sorry, I'm jumping around a little bit, but I've basically stated these bullet points already. So we're going to generate a random secret value, and we're going to save it somewhere in some storage somewhere. It doesn't really matter where that is. We just need to make sure we can get to it later. In the function prologue, we're going to add a little bit of extra code that says, put an extra value on the stack, and that extra value is taken from the canary storage. In the function epilogue, we're going to look at that value of the stack and compare it against whatever's in our canary storage. And if that value has changed, then we're going to assume something has gone wrong. We will crash. And if not, then we know that the program probably was not attacked. So we can just continue execution as before. So some properties that we want from the stack canary. The stack canary needs to be different every time the program is run. But it's, in this case, we're going to say it's the same every time the canary runs, every time the, it's unique every time the program runs. So it's different every time the program runs, but for all functions, it's the same value. So there's the same value on the stack a bunch of times, but those values change if we rerun the program. The canary value also has a null byte in it. So this is because we don't want the attacker learning the value of the stack canary. If the attacker learns the value of this canary, then they can just use it to overwrite it with itself, and we'll get into that in a moment. But we include a null byte in it to prevent something like a printf or a strcpy from copying that canary value to somewhere else. Okay, so this is a diagram of what you'll normally see when you're dealing with stack canaries. We have the same code as before, so it's just the name buffer and the gets function. But now we've put name and then the canary and then the rest of the code. So we've added a little bit of canary code here. Basically, we just say load the canary from our canary storage here, store it into EAX, and then store EAX into 4 bytes below the EBP. The x86 specifically isn't too important, and it'll look different in different places, but this is just something that you might expect to see. At the end, we load the canary value, we compare it against the value that we have saved in our canary storage, and if the comparison was not the same, so jump if not equal, then we jump to some code that crashes the program, jump to the canary fit. Because we're assuming that most functions are going to start at lower memory addresses and write to higher memory addresses, we can infer that, for example, this getS, in order to overwrite the RIP, it first has to overwrite the SFP, and before it can overwrite the SFP, it has to overwrite the canary. So we have to write in this direction, and there's no way for us to just prevent writing. There's no way for us to overwrite this RIP without overwriting the canary. So that's the main idea behind this attack. As a side note, instead of allocating 20 bytes on the stack, we are now allocating 24 because we need to save that canary. So just a side note, It's something that you might have noticed if you were paying really close attention to the x86, which you don't have to. Okay, so let's talk about efficiency for the stack canary. Because we have a couple extra instructions, it means that your programs are going to run a little bit slower, but in almost all applications, it's not going to matter. In fact, I think all applications, well, not all applications, but most of the applications that we run today, they already have stack canaries enabled by the compiler. So you're already living with stack canaries, whether you realize it or not. It's a very cheap way to stop a lot of the common attacks because most of the attacks are going to start from the lower memory address and write upwards. So they're going to have to write past the stack canary before it overwrites the RIP. Questions on how this works? All right. I have a question in private chat, so I won't say the name, but there's a question that says, couldn't the attacker look into memory and just see what the canary value is? That's a really good observation. It seems pretty simple that the attacker could just go, oh, I'll just look in the canary storage and get the value for it myself. The idea here is that the attacker doesn't have direct access into the memory of the program. And in order to read from anywhere that they want, either they have to find a vulnerability that lets them do that, or they have to execute their own code that reads from the canary storage. But the attacker can't execute their own code until they've overwritten the RIP. Until then, they're just stuck with the standard flow of execution. They're just stuck with this vulnerable function here. And none of this directly spills the value of the canary to the attacker. All right. So we talked about efficiency. These are the main ways that we will subvert stack canary. So we already touched on a couple of this earlier in the question, but first you can leak the value of the stack canary. If you're able to learn what the value of the stack canary is, and we'll go into how we do that in a moment, then you can just overwrite the value of the stack canary with itself. And then when the program goes to check it, it sees, oh, the value is still the same as before. So I'm going to assume that there hasn't been an exploit here. Some exploits, some vulnerabilities will also let us bypass the value of the canary. So if we can write to a random address of the attacker's choosing rather than a sequential write, such as getS, then we can just say, okay, start writing at the RIP and just don't even touch the stack canary, and that will allow the check to pass. Finally, we have what's probably the least elegant solution, but one that's definitely used in practice, is you can guess the value of the canary. There are only 32 bits on the stack, and 8 of them are a null byte. So there are only 24 bits that you need to guess. I'll get into that in a moment. So first, leaking the canary. Any vulnerability that allows the memory on the stack to be leaked is potentially a vulnerability that you can use to leak the value of the canary. For example, remember, a format string vulnerability lets you just continually print out 4 bytes on the stack using %x or %d. If you have a format string vulnerability, then the attacker could just use that, learn the value of the stack canary, and then in the getS, they will place the value of the canary in the correct place such that you overwrite the canary with itself. This is something that you will have exposure to in project 1. Yeah, once you learn it, you overwrite the canary with itself. The second way is to bypass the stack canary. So again, most functions rely on writing to memory from low to high in consecutive addresses on the stack. But a lot of stack canary, or but some attacks don't require this. Some attacks allow you to write to memory in a random fashion. Random just as in you get to choose the address rather than being a consecutive write. So if you write around the canary, then the canary check will pass. And something like a format string vulnerability, again, lets an attacker write to any location in memory. If you recall the %n in a format string, that writes the number of bytes written to so far. And that allows the attacker to write any value to memory that they want. Something like heap overflows also won't overwrite a stack canary because the stack canaries are on the stack and heap overflows take place on the heap. Same thing with the vtable. The vtable exists in static memory, I believe. So again, there's no stack canary there because it's in static memory. There's a question how you would figure out the address of the canary to write around it. If I go back a little bit. So remember how on the stack, everything is always going to be at the same address relative to everything else. So I know that the canary is 20 bytes from the start of name. So in this case, my exploit would be something like a times 20 plus the value of the canary, so that the canary is overwritten with itself, plus 4 more dummy bytes to overwrite the SFP, plus my malicious RIP that I want to overwrite. Does that make sense? Yeah. All right. Finally, we'll talk a bit about guessing the canary. So on 32-bit systems, there are only 24 bits to guess because 8 of the bits are always 0 as a null byte. On 64-bit systems, we have 56 bits to guess, which is a little bit better. The feasibility of that is a little bit more up in the air. On 32-bit systems, which only have about 16 million possibilities, you can feasibly brute force this in a reasonable amount of time. It might take a couple hours, but at some point you will have exploited the program. On 64-bit systems, probably not happening. So if you're running the program online, then, or if you're running the program offline, if you're running it on your own program, there's nothing stopping you from running the program 16 million times. And if you have a multi-threaded system, you can even run the program multiple times at the same time to increase the number of tries that you get. If it's running on a remote server, so let's say you're interacting with a server over the internet, then your programs might be, then your queries might be slower and the server might notice and say, hey, I think you're trying to exploit me, stop it. So it will end up rejecting your request and maybe it's not possible. We also might have to deal with timeouts. So on a remote server, if the program has, or if the server stops you from interacting with the program for a given amount of time, that's called a timeout. If there are no timeouts, then 10,000 tries would take 10,000 tries per second would mean that 24 bits can be brute forced in about 30 minutes. But if you have even a tenth of a second as your timeout, then suddenly it's going to take 3 weeks. And there are even more complicated ways of doing this. If 10 consecutive failures means you get a 10-minute timeout, basically that averages to 1 minute per try, that's going to take you 32 years. And if you have an exponentially growing timeout, so say your timeout doubles every time you fail, then it's just not happening. It's not. 2 to the 2 to the 24 is a number that's far too large to comprehend. All right, does this all make sense, how stack canaries work and how we get around them? All right, there's a lot of information to cover today, so I'm sorry if I'm going really quickly, but yeah, there's just a lot. The second mitigation that we'll talk about when we're dealing with preventing the RIP from being overridden is called pointer authentication. So in a 32-bit processor, remember that the integers and pointers are 32 bits long, and we can only address 4 gigabytes of memory. But on a 64-bit processor, in theory, if we had 64 bits, we can address 18 billion gigabytes of memory. That is too much. My computer does not have that memory. I don't think that much memory exists in the world right now. Maybe it does, I'm not sure. But even the best modern computers only really need 2 to the 42 bytes nowadays, which is 4 terabytes, which is still unfathomable for me, but maybe in the realm of possibility. This means that if only 42 bits of memory, if only 42 bits are needed to address all of memory, then we have some bits left over that we can use to somehow store some secret value. So this is where we get into pointer authentication. For stack canaries, we had a secret value that was stored in memory. And if the value changes, we crash. Now, instead of placing the secret value below it in memory, we're going to store the value within the pointer itself, within those 22 bits that we weren't using before. When we store the secret value in memory, we're going to call the secret value the pointer authentication code, or the PAC. Before we use the pointer, we'll check and make sure, is this PAC still valid? And if the PAC isn't valid, then we crash. Else we assume, okay, this is probably unmodified, and then we'll continue along our day. And anything that is a pointer can have this. So on 64-bit systems, everything's a little bit larger, twice as large actually. But the RIP, SFP, and basically any other pointer on the stack can have this because those are all pointers and we can authenticate those pointers. We can also do this on the heap, and we can do this, well, I guess it's mainly on the heap and in the static data sections where we might also store pointers. So what do we want from this PAC? We want to make sure that if the address changes, then the PAC is no longer valid. So if we have this address here that ends in a 0 and this address here that ends in a 4, we want to make sure that those have completely different PAC values. We also want to make sure that no one can generate a PAC for an address. If the attacker is able to just figure out what the PAC for a different address would be, then they can just overwrite that pointer and overwrite the PAC so that it's still valid. So we want to make sure only the CPU can do it. And the CPU has this value called the master secret. We'll talk a little bit more about how this works in the cryptography unit, but basically the attacker can't generate a PAC without the master secret, and the attacker can't generate a PAC using a different PAC. The CPU's master secret is not accessible to the program. So someone brought up a good observation someone brought up a good observation earlier that, well, maybe you can still just read the canary value from memory. But in this case, the CPU's master secret isn't stored in memory. It's stored in the CPU itself. So no one has access to the secret. No one can even read the value of the secret. We can only ask the CPU to generate the PAC for us. This is in contrast to canaries, where we can leak the value. We talked about this. All right, that sounds amazing. How do we break this? So the main thing that we want to do is we want to trick the program into generating a PAC for some address. If we can trick it to generate a PAC for us, then we can just use that PAC, place it in the RIP, and then it's going to be marked as valid. We can also try to learn the master secret. It depends on the implementation. Some implementations might allow the master secret to be learned, and the operating system is the one that has to set up the secret. So if there's a vulnerability in the OS that leaks the secret, then suddenly we can learn the secret and generate our own PACs. Finally, we can brute force. So similar to earlier, we only have 22 bits. This is even less than in the 32-bit stack canary where we had 24 bits. So this is only 4 million tries. So this is maybe feasible depending on your threat model. Again, whether it's online or offline and whether there's a timeout. Finally, pointer reuse. So remember, each pointer has its own PAC. If we change the value of the pointer, we change the value of the PAC. But if that pointer is used somewhere else, the attacker can just scoop up that PAC, place it in the RIP, and use that same address, assuming that there's shellcode at that malicious address. So even though the attacker can't generate their own PACs, the attacker can still use or abuse already existing PACs in memory for already authenticated pointers. Okay, I'm gonna skip past this because it's blue and we're really out of time. If you're curious, you can go back. It basically just talks about how we defend against those subversion techniques we just talked about, but you don't have to worry about it too much. Finally, the last defense that we have is ASLR. So here, instead of preventing the attacker from overwriting the RIP, we're going to go even farther back, and we're going to prevent the attacker from knowing the address of anything in memory. This is called address space layout randomization because we're randomizing the layout of the address space. So in the standard x86 memory layout, we have these segments of memory. Sorry, took me a moment to say that. In theory, it looks like this, but in fact, there are really, really large gaps between the segments of memory here. There's maybe I don't know, a gigabyte between the code and the data, or not the code and the data, between, say, the heap and the stack. And there are gaps between other segments as well. So in fact, these are really just small slivers of a giant 4 gigabyte address space in 32-bit. So what we can do is say, instead of putting the stack up here, let's put it down here. And instead of putting the data here, we'll put it here. Now, how does this help us? Remember that the attacker needs to know the address of their shellcode so that they can overwrite the RIP with that address. If the segments of memory are shuffled around every time the program is run, then the attacker, in theory, doesn't have any way of knowing, even if they wrote shellcode into memory, they have no idea where that shellcode is. The address of that is unknown, so they can't overwrite the RIP. If we randomize the stack, we can't place a shellcode on the stack without knowing the address of the stack. If we randomize the heap, same thing. We can't place shellcode in the heap without knowing the address of the heap. And if we randomize the code, then we can't construct ROP chain. So go back for a moment and think about non-executable pages. We needed to know the addresses of the different gadgets in memory so that we could put them together and execute the equivalent of our own code. But if we don't know where any of the code is, and if that code changes, if that code address changes every time we run the program, then suddenly our ROP chain is broken. So the thing to keep in mind is we're only randomizing the segments. The relative addresses within the segments is always going to be the same. For example, the RIP is always going to be 4 bytes above the SFP. Does this make sense, how this defense works? Yeah. Any questions? All right. In terms of efficiency, so can the hacker use relative addresses? I'll go back for a moment. So remember that when the RIP is placed on the stack, that's going to be treated as an absolute address. The CPU says, okay, I'm going to jump back to the instructions at this exact address in memory. So there's no way for us to say, oh, this time we want the RIP to be a relative jump. It's always going to be absolute. Couldn't you use a print format attack to find random addresses? Yes, you're getting ahead of me, but we will get into how to subvert ASLR in a moment. Very good question and observation, respectively, though. But Thomas, does that answer your question? Okay. If not, we'll also talk about how relative addresses can be used to exploit code in a moment. So going back to efficiency for ASLR, again, remember that programs are dynamically linked at runtime. So we grab pieces of code from other libraries and put them together and put them all in memory. We're already doing this. We're already placing code, reading it from files and placing it in memory. So we can just add a little bit of extra code to say, oh, now can you please place it in a different spot every time and give different addresses to the program each time. So we're already doing this work. This means that we don't really have any overhead because we already have to do this. So we're just going to do it in a different way every time we run the program. All right, how do we subvert ASLR? How do we break this? First, if we leak the address of a pointer whose address relative to your shellcode is known, then you can learn the address of your shellcode. I know that, oh, if I know that my shellcode is 4 bytes above the RIP, and somehow I learn what the value of the RIP is, then I'll just add 4 to it and I'll infer, okay, that must be the address of my shellcode. Usually this will be done with stack pointers. So the RIP is not a pointer to the stack. The RIP is a pointer on the stack, but it doesn't point to the stack. Remember, it points to the code. The SFP is usually a more vulnerable target. So the SFP, remember, points to the previous SFP, just because that's how the function prologues are set up. So because we know that the SFP points somewhere on the stack, and we can always guess, okay, our shellcode is some number of bytes below or above that value of the SFP, then we can learn the address of our shellcode that way. The RIP also allows us to leak the location of the caller. So if we were executing some sort of ROP chain attack, or maybe a return to libc attack, this would also let us subvert, this would also let us execute those attacks in the same way. Finally, you'll have seen these before, but we can use brute force. Randomization only really happens on page boundaries. So if you're not familiar with pages, it doesn't matter too much, but the thing to keep in mind is that the first or the last 12 bits of any address, of any starting address, are always going to be the same. This means we only have about 2 to the 20 pages to play with, 20 bits. So this is, again, feasibly brute forced. In this case, this is only really a million possibilities. For 64-bit addressing, it's a little bit better. Again, usually we're going to be dealing with smaller actual addresses. So 48 bits minus 12, because all the last 12 bits are the same, are always the same. Then we have 36 bits, which is 2 to the 36, which is a little bit better. So I guess the common theme here is we can always solve things through brute force, but we can't always solve them efficiently. All right. This is a little bit of practice with the actual, I guess it's not practice, I've given you the answer, but this is a bit of an example of how you would infer what the address of your shellcode is. So, oh, I know what happened. The transitions weren't set up correctly. All right, that's okay. In this case, we know that the SFP points to the stack. This is what I was saying earlier. If we wanted to print the value of the SFP, as Nicholas mentioned in chat, we can use a printf vulnerability or a format string vulnerability to leak the value of this SFP. In this case, we know that this is the 0th arg, so printf will assume that this SFP is the first arg. So now we learn that the value of this SFP is BFFFF0404, just as an example. Okay. Yeah. Sorry, this is really out of order, so it's messing with me. The output is 0408, so it's saying the value is 0408, and that's pointing here. So if we place our shellcode, or if we want to learn the address of secret, we know that it's 4 bytes below. So this SFP is pointing up here. The value of this SFP is 0408, and we know that secret is 4 bytes below where SFP points. So the address of secret is 0404. We would do the same thing with shellcode if we wanted to overwrite the RIP with the address of shellcode. Sorry about that. The transitions were a little wonky. And I think the transitions after here are non-existent. So you're just going to get a really long wall of text. Sorry about that.
I think maybe if you close the lecture and then reopen it, because I did add these at some point.
I will try that.
Okay.
All right. Let's see. Yes, it looked like it worked. All right. So remember that we can use multiple mitigations together. This is the same defense in depth principle that we were talking about on Monday. This is the idea of synergistic protection. We're using one mitigation, and that mitigation is actually helping strengthen the other mitigation. So this is actually a case where using both of them combined is better than using either of them individually, and it's basically greater than the sum of its parts. We need to force the attacker to find multiple vulnerabilities in order to exploit the program. So because we have, say, 2 defenses enabled, now the attacker has to find both a ROP chain to compile, for example, and has to leak a stack pointer in order to actually exploit the program. So again, we're not making it impossible. We're just making it harder to exploit the program. Defense in depth. Okay, we're going to use the example of combining ASLR and non-executable pages, which I mentioned earlier. The attacker can't write their own shellcode because of non-executable pages. The attacker can't use existing code in memory because they don't know the addresses of the code. So in this case, again, they would have to find 2 vulnerabilities. One to leak the address of code so that they can put together their ROP chain in real time. And the actual ROP chain itself, because they need to subvert W XOR X, or non-executable pages. Sorry about that. Talking about this out of order again. Yes, the attacker needs to find 2 vulnerabilities. All right, so let's talk about an example of Apple's iOS. So iOS uses many memory safety defenses. It uses all of them and a couple more that we haven't really talked about. They use ASLR for both programs, and they use it for the operating system itself. They use non-executable pages wherever it's possible. They sandbox the application, so even if it's hacked, it can't damage the rest of the system. And it uses the operating system as the TCP to enforce the sandboxing. This led to something known as the Trident exploit. So this was developed by the NSO group. They sell exploits and spyware to people to exploit iPhones. First, they would exploit Safari with a memory corruption vulnerability, which allows them to execute arbitrary code within the sandbox. That's the first problem. Then they exploited another vulnerability in order to read the kernel stack. So they are able to read memory in the operating system through some other vulnerability. And they were able to exploit another vulnerability in the kernel to execute arbitrary code. So they needed 3 separate exploits to actually be able to break into the iPhone, basically. So the takeaway here is if we combine mitigation, it forces the attacker to find multiple vulnerabilities. It makes it harder, but again, it's not impossible because this exploit was actually developed. So finally, we're going to talk a little bit about enabling mitigation. So many mitigations are effectively free. We talked about how most of them don't actually require any additional or any performance penalty. And some of them are just really minor in terms of the performance penalty. Unfortunately, the programmer has to manually enable these mitigations. For example, we have to enable ASLR and non-executable pages when we're running a program. Or we have to set a flag in the compiler to insert that extra code to check stack canaries. So unfortunately, the default is that a lot of these mitigations aren't going to be enabled by default. And again, you can think back to lecture 1 where we talked about choosing fail-safe defaults. In this case, the default is disabling the mitigation. And because programmers are lazy and humans like convenience, this is what we're going to go with. Yes, we'll call these security principles. So let's talk about Cisco. We talked about this a little bit last time, I think, but we're talking about it again. So we talked about their adaptive security appliances. This is just a network security device that doesn't matter too much. Here's the thing. The mitigations used by the adaptive security appliances were basically non-existent. They had no stack canaries, no non-executable pages, no ASLR, and this made it really easy for the NSA to exploit. Again, we talked about the exploit. I forget the name of it off the top of my head. I think it was extra bacon. Yeah. And I guess to complete that, it was really easy for the NSA to exploit this because they didn't enable mitigations. There are a couple other stories here. This one's actually from really recently. So if you have kept up with security news at all, we have a program called sudo. I actually don't know what the correct way of saying that is. It's basically a program that lets you run commands as root, as the most privileged user on the system. And there was actually a heap overflow vulnerability in sudo. So this was on most major operating systems. And the issue here is that a lot of Internet of Things devices, basically say a smart speaker or maybe a smart light bulb, anything that has the word smart in it, they run some sort of Unix operating system and they have sudo installed. And because these IoT devices generally don't enable security mitigations, it's really easy for a user to exploit this vulnerability in sudo to, I guess, take over your device, possibly gain a foothold in your network and take over your network. So yes, well, maybe don't uninstall sudo. That might be an issue, but up to you. But that's all that we have for you today. I know that it was a lot and it's really dense, and somehow we're amazingly ending on time. So yeah, but we talked about memory safe languages. If you use a memory safe language, it stops all memory safety vulnerabilities, and you should probably use them unless you're writing an operating system, because most likely that performance, you're never going to see a real difference in that performance. We just use it because existing code uses it. We talked about how to write memory safe code. So make sure you're using the correct memory safe functions, and make sure you have the discipline to add the checks that you need and to use the functions that you're supposed to use. We talked a bit about tools that we can use to build secure software, tools that we can use to test for vulnerabilities, and how to keep external libraries updated so that other people's code doesn't end up breaking your program. And then we talked about all the mitigations. We talked about non-executable pages, which prevents memory from being both written to and executed at the same time. And we can subvert this by using existing code, either in a return to libc attack or in a ROP chain attack. Talked about stack canaries, so that places a value on the stack, and if the stack value changes, then we know that something probably overwrote the RIP and will automatically crash. But the attacker can get around this by overwriting the canary, can get around this by leaking the value of the canary, or by just brute forcing it. We talked about pointer auth. So this is basically an improved version of stack canaries where we store the secret value in the pointer itself. And that secret value is only valid for that pointer. And it's different for every single pointer, so that the attacker can't change the address pretty much at all unless they get the CPU to either authenticate to generate a pack for an address that the attacker wants to use, or use an existing pack in memory somewhere and copying it into place. And we talked about ASLR. So basically you shuffle all the different segments of memory around to make it hard for the attacker to know actually where their shellcode is placed. But you can break this by leaking addresses or, again, brute forcing the addresses. And finally, we talked about combining mitigations. So how can we put together mitigations in a way that forces, or not how can we, but the fact that we put together mitigations in order to force the attacker to find multiple vulnerabilities and just make the attacker's life a really difficult time. So yeah, that is all that we have for you today. We ended 2 minutes early, which I am actually kind of amazed about. So yeah, any final questions about anything before we head out?
Someone asked about briefly looking at the blue slides from earlier. So since
sure,
we have 60
look
seconds,
into that. None of this is necessary, so feel free to leave now. I'll keep the recording going just because some other people might be interested. Wow, there are a lot of slides here. Hold on.
This is definitely maybe the longest, if not.
Karen, do you have the slide number of the first slide I skipped?
Nope, but I will look for it for you.
All right, we're just gonna blitz past.
It was the patch treadmill, so I think you're really close. Oh, you just skipped over it. Yeah, here you go.
Oh yeah, these are really just a couple of stories of basically trying to hit home the point that security patches are really important and they can break things and they come out really often. So this story is from Java. If you've used that programming language, it receives a lot of updates. And one of the Java updates actually ended up removing Java 6 and ended up breaking a lot of programs that relied on Java 6. So the takeaway here is security patches can break older systems. Here, I actually find this one kind of amusing because this is Light Patch Tuesday. The Light Patch Tuesday only had 4 security bulletins for this month. So yeah, patches get released really often and you need to make sure you're keeping up to date with them. And only one of them was rated critical in Light Patch Thursday. So yeah. Finally, this one was Ruby on Rails. This was talking about a vulnerability that came up and they knew that people were developing an exploit for that vulnerability at the time. And the patch for it was already released. So at this point, it was basically a race between the people maintaining or the users using Ruby on Rails and the developers developing the exploit to make sure that they updated before the exploit was truly out. So it's really a race to make sure that your things are always up to date. So always keep your software up to date. That is all I will have to say about that. And then I think we skipped some stuff about pointer auth, I think, right?
Oh yeah, there are some fancy techniques.
Yeah, if you really want to know about pointer auth, feel free to stick around for the next 10 minutes. But again, everything here.
I don't think it'll take 10 minutes. Yeah.
We'll see. So in pointer auth, the way to subvert pointer auth is to prevent or to use a pack that's already been generated. So what we're going to do is we actually have 5 secrets in ARM's implementation, which is kind of the only implementation. ARM has 5 secrets. It has 2 of them for instruction pointers, 2 of them for data pointers, and 1 of them just for general purpose. So this means that if the program has a data pointer pointing to our shellcode, we can't use that as the RIP because the RIP is an instruction pointer. It needs a different secret to actually verify correctly. So that just basically means that the attacker not only needs a pack for the right address, it also needs a pack for the right address and the right secret. And the other thing that we do is our pack is going to include some context. It's a little bit complicated, and I think this one's hard to understand unless you're familiar with Max, which again we'll get into. I think we'll get into it by next week. I'm not sure. But basically, the pack only works if the pointer value has stayed the same and the address of that pointer, so wherever that pointer is located, has also stayed the same. So if I store a pointer A at memory address B on the stack, then if I move that pointer to a different memory address, but I keep the same value, that's still going to fail because we moved it to a different address C, and basically the pack for A at B is different from the pack for A at C. So it basically prevents the attacker from reusing pointers as much as possible. And pointer authentication is really only implemented on ARM. The latest Apple chips are ARM, which is only going to support versions of ARM that have pointer authentication implemented. So this is actually a benefit for Apple as they move to ARM systems, because they can take advantage of this pointer authentication, and they can take advantage of more complicated instructions that don't work if your CPU doesn't support pointer authentication, because Apple knows that all Apple computers are going to support it. So they pretty much don't have any performance overhead, unlike if they wanted to do it in a way that works on older CPUs. x86 doesn't have a similar defense. I have no idea if it will. I haven't looked into it, but yeah, I think there used to be a couple slides that went into exactly how ARM implemented it, but in the interest of time, we took those slides out entirely. But yeah, that's what you missed. And if you stuck around, here it is. So yeah. Any final questions? I know there aren't many of us anymore, but if you have any questions on anything, feel free to ask. All right. Okay, see you everyone. Enjoy your weekend.